set? Yes.
Yes, sir. So we can start, sir.
Can we start?
Yes, sir. Hello, everyone. A very good morning to one and all present here. On the behalf of Team Footprints, I, Param Patel, committee member of Footprints, welcomes you all. First of all, we would like to thank our title sponsor IMS and Kaleidoscope sponsor Excel for their support. From the medieval age, we humans have always been curious about outer space and have made significant growth in the field of astronomy and physics. Although some of the question remains unanswered, like is life possible out the space? Are there any habitable planets? Are aliens real? Or is it just a myth? After completion of this lecture, you will get answers of few of these questions. Now I would like to introduce today's guest speaker, Roger Hunter, sir. After his tenure at US Air Force, Colonel Hunter worked on various assignments, including program manager for the XSS-10 microsatellite technology demonstration for Air Force Research Laboratory. He joined NASA, where he worked as program manager for the Kepler mission. Kepler mission is the first mission capable of finding potentially habitable planets in the Milky Way galaxy outside our solar system. We have Chetan Limbachia sir in this meeting, who is head of Applied Physics Department and also Dean of Students. So I would like to request Chetan sir to welcome our guest speaker Roger sir and add some work in this occasion.
Thank you, Param. And good evening, Colonel Hunter, Roger Hunter. Very pleased to have you back on our Footprint program. So, while I welcome you to the Footprint program, as you know, that Footprint is one of the flagship events of our technology faculty, which we fondly call TECO. So, the Faculty of Technology and Engineering, which is one of the 14 faculties of the MS University of Vadodara, actually the students of these faculty are so vibrant and so active, and we are quite proud of our students. They have been organizing this event and completely organized. This event is completely organized by students, and that makes it quite unique. Our role, the role from the teachers is minimal actually. We are only supporting them. So this on the 21st edition of the Footprint, I congratulate our Footprint team for having invited stalwarts like Colonel Roger Hunter, who is a scientist at the very reputed, coveted space agency NASA. And NASA and ISRO have been doing the research in the space programs for many decades. And we in Gujarat, the Vadodara, which is a city in Gujarat, is the place from where it all began for ISRO. I would like to add to, brief to Roger Hunter, that Dr. Vikram Sarabhai initiated the space programs from Ahmedabad, one of the cities in Gujarat state of the country. And then it actually prospered and grew into a big ISRO organization, which we are very much proud of. So, as we all know, NASA is the single space agency which has done quite dominating work in the space programs, in the planetary programs, etc. So, our scientist, Roger Hunter, will brief all of you students for today's topic, which are related to spacecraft technology, small spacecraft technology. And it will be great. It will be quite interacting session. I'm sure it will be illuminating, and all of our students will be highly benefited by this session. So, and I assure our guest, Colonel Hunter, that our students will take not only interest in your talk, but later on also they will bother you, they will try to interact with you, because many of our students of various engineering branches have varied interest even in the space technology and space programs. So from the Faculty of Technology and Engineering, from the Maharaja Sayajirao University of Baroda, I welcome you to the program. Thank you so much. Yes.
Thank you, sir. Now, I would request Roger Hunter, sir, to start his presentation and request all the participants to keep patience. And if you have any questions, kindly mention them in the Google form given in the chat box. So you can start.
Thank you so much. Can you hear me?
Yes,
Yes.
sir. You're all
All right,
audible.
thank you. And I'm sharing my screen. It's unfortunate that I cannot join you in person because of the ongoing COVID-19 pandemic, but we will come out of this one day, and I hope to visit India again, perhaps
Yes,
visit
sir.
with
We would be
you
very
at your
glad.
university. Thank you. So I want to, my lecture this evening is basically divided into three segments. I do want to talk about my current position and what we're doing in small spacecraft technology development within NASA. Later on, I do want to touch on the final results from the Kepler mission that I had the honor and privilege to be the program manager for a number of years. And at the end of this, I would like to draw your attention to some upcoming NASA missions that I think you might find interesting. So let's kick it off and let's talk about NASA small spacecraft activities. And of course, NASA is all about science and exploration, and we are using small spacecraft to assist us in ongoing and future science and exploration missions. But we also have an area in space technology development, which I'm running with a team at NASA, and this is spread across basically a number of the centers within NASA to develop and demonstrate new upcoming technologies that are emerging from either industry or from academia or from other government agencies that will make our science and exploration missions for the future even more productive using small spacecraft. These are our objectives, basically because of where the technology and electronics revolution has brought us. We are looking at the miniaturization of electronics and technologies that we think are going to continue to allow us to lower the cost of space missions for the future, reduce the time it takes to develop a space mission. In some cases, we think this is going to enable us to think about new mission architectures. For example, if you think about Hubble, is a singular spacecraft that's conducting a singular science mission. And we are now thinking of using many small spacecraft to actually conduct science exploration missions by conducting multi-point science data collection around a science object of interest. We want to get small spacecraft out of low Earth orbit because that's where we've been operating mostly since we started embracing small spacecraft, and we are starting to use them for new destinations. I will show you some some information later on how we're going to use small spacecraft to help us out with cislunar missions. And we've already sent 2 CubeSat class spacecraft to escort the NASA InSight lander when it's made its journey to Mars 2 to 3 years ago. And there's also the opportunity for us to look at the augmenting spacecraft missions for the future using small spacecraft. For example, if you could imagine a mothership that is loaded with small spacecraft that makes a journey to Enceladus, that moon around Saturn, around which the Cassini spacecraft and Hubble have seen geysers arising from the surface of that moon, that mothership with its small spacecraft could basically perform a maneuver around Enceladus and drop those small spacecraft into orbits around Enceladus and then collect information against those geysers that have been seen coming off of that moon, or even drop some landers onto the surface of the moon itself to conduct science to determine, is there life in the water that we believe is underneath the surface of that moon. So where do we get the technology development pipeline? As you might guess, it's from the usual suspects. Of course, NASA is good at forming partnerships with many universities. We form partnerships with small businesses. We also conduct public-private partnerships, sometimes with much larger businesses, for example, like a Northrop Grumman or a Raytheon. And in the end, when those technologies have advanced to a readiness level that we think they are now viable to be flown in space, we will conduct a technology demonstration in space to verify that the technology is working properly before we hand it over to the Science Mission Directorate within NASA to conduct those future science or exploration missions. Now, I don't want to belabor this chart too much, but I just want to give you an idea of the amount of money that NASA invests with universities across a number of states within the United States, and we align those universities with all the NASA centers to provide expertise and advice and feedback to the universities that are conducting these technology developments that we find useful, or we may find useful for future missions. And so I just want to leave you with this thought that we will continue to do this. This has been a very profitable area for us, investing with universities as they develop technologies. It also gives us a hotbed for where we recruit our future scientists and engineers. Now I want to talk about just some recently completed UClass meaning CubeSat class missions, to give you an idea of where we're headed. The things that we're focusing on mostly are improving the communications, the power, the propulsion, and the processing capability of these small spacecraft, so that they will become much more valuable tools for us to conduct these science and exploration missions in the future as we move out of the low Earth orbit and into cislunar space and into planetary space, and who knows, maybe sometime in the future into interstellar science and exploration missions. There are two spacecraft that are depicted in this image that I'm sharing with you, and you can see fingers or hands in the picture to give you a scale. The one on the left was called ISARA, for Integrated Solar Array and Reflector Array Antenna. We were demonstrating two different technologies in this particular 3U spacecraft. One was that new flat panel antenna that you see there, and the other one was a Ka-band communications capability that we have now downsized so that it can fit onto CubeSat class spacecraft. The first time NASA had used Ka-band communications on the largest spacecraft was actually on Kepler, the mission that I ran for a number of years. The spacecraft on the right is the first time we demonstrated laser comm, or optical communications, from a spacecraft that's only about the size of a tissue box. And this was a twin mission. There was two spacecraft identical to each other. And I'll talk a little bit more about those in a moment. But both of these were very successful in demonstrating Ka-band communications on the one on the left, and we were able to actually demonstrate 100 megabits per second of data transmission, which is pretty impressive for a little 3U size spacecraft. And on the right, with the optical communications and sensor demonstration, we actually demonstrated 200 megabits per second during the mission objectives, and both were very successful. But there's one thing we do in my organization, and that is we try to take advantage of the agility of the timelines and when we're developing these spacecraft. The one on the left, we had some empty space on board at 3U, if you can imagine that. And the Aerospace Corporation brought to us a 1U size, or a 10 by 10 by 10 centimeter size multispectral imager, and they asked if we could host it on that spacecraft before we launched. And in coordination with JPL, we said we could, and we did allow the integration of that multispectral imager on that spacecraft, but we mentioned to Aerospace Corporation that our experiment comes first, and we had to demonstrate the Ka-band communications and the viability of that flat panel antenna before we would allow the multispectral imager to be turned on. And I want to show you some images that we took with that, because this gives you an impression of the ability of these very small spacecraft to actually do pretty good Earth observation of things or events that are occurring on the surface of the planet. So, before I show you the next image, once again, these were mostly oriented toward improving communications for low Earth orbiting small spacecraft, and they worked perfectly. 100 megabits per second for the one on the left, 200 megabits per second on the one on the right. Now I'm going to show you images that we took with the multispectral imager that we included in the spacecraft on the left, and we turned it on after we finished those Ka-band communications. Now, you probably, if you watch CNN, you probably were aware of the huge forest fires that were dominating Northern California in late 2018. And these images I'm showing you on this chart were images that we took with that 1U size multispectral imager of what is called the Campfire. That was the name of the fire as it was raging in Northern California. And you can see the shortwave infrared and the long wave infrared images here. And I want to point out to you, if you can see my cursor moving on the image on the left, right in the center of it, we were coming up overnight over this hot spots in Northern California. And right there in the center of that image on the left is the town of Paradise. And those are the burning remnants of the town. There's a population of about 18,000 people there, and this town burned to the ground. And it was sobering to see this image, because you were realizing that there were a number of lives that were lost in this fire, and it was very destructive. But you could see this from 450 kilometers above the surface of the Earth with a small 1U size multispectral imager as you were flying up over the Earth at 17,500 nautical miles an hour, and you're imaging this at night. So the next thing I want to show you, and I don't know if this will, if you can see the animation here, but this shows you the optical communications and sensor demonstration animation of this this mission. And of course, this the animator here shows the spacecraft initially going through its initial checkout phases, then doing the optical communications demonstration to a target on the ground. But the other thing we did with these two spacecraft is that we want to show proximity operations around each other. And we had these spacecraft as far apart as 470 kilometers and as close as 6 meters. And we had a very small propulsion system on board each other. And it was just water. We were just using water as the propellant on board. And we would heat the water up in like a little steam engine and go put, put, put around each other. And it's very successful. But sometimes what we do once we get these spacecraft on orbit, we like to do a little extra credit. And that's one of the things we did with this particular mission. And before I run this animation, let me set this up for you. You remember the image I just showed you earlier of the spacecraft that did the Ka-band communications and had the multispectral imager. And then of course, the two spacecraft that have the lasers on board. Our engineers asked, hey, could we demonstrate something else that we didn't plan to do? And I said, what do you have in mind? And it said, let's see if we could turn the OSIRIS spacecraft on its side and point the Cumulus or the multispectral imager in the direction of those two small spacecraft that have the lasers on board, and then see if we can hit the Cumulus or multispectral imager and keep it on target. And we said, oh, that sounds like an interesting experiment. Let's do that. So let me set this up. If you can see this image, before I start the animation, what you see on the right, of course, is the limb of the Earth. And this hot spot you see in the middle, that is not a laser. That is an infrared star that's radiating very hot. And so the multispectral imager that was on board OSIRIS, which we called Cumulus, was tracking the star. And of course, this animation is sped up a bit so you can see the animation. You will see that star move from about the 10 o'clock position to around the 4 o'clock position. It is not a UFO, it's just an IR star. But then right in the center of this image, right around where you can see my cursor moving, is where you'll see the laser light up. And so let me run the animation. So you'll see the laser now light up. And we did this several times. The first time we would just take a laser and sweep it across the focal plane, just so we can say, hey, we can hit it. And these spacecraft were at a distance of about 2,200 kilometers, which was impressive. But there were several subsequent tests in which we were able to keep the laser on the target for over 3.5 minutes. Now that's important for a number of reasons. Think of a constellation of spacecraft that you have now placed around the moon or Mars, and you want to be sharing a lot of information with the settlements or investigation sites or science sites that are on the surface of the moon or Mars. And you want to keep those spacecraft in constant communication, and you can relay that information. So this proves that you can keep a laser on target for more than just a fraction of a second. You can do it for several minutes. And you can then use your imagination how that can be used for other science or exploration missions. So that demonstration between OCSD and OSIRIS multispectral imager payload, which is called the Cumulus, were some recent demonstrations that we completed. Now I'd like to talk about some that are coming up that I will share with you. And some of these are ongoing now as we speak. The one on the left is a series of 6 U-size spacecraft. 3U of the spacecraft is, of course, what drives the spacecraft itself, to all the avionics, the propulsion, or the electrical power distribution, things like that. And of course, half of the spacecraft is reserved for a new technology that we think is going to be valuable for future small spacecraft. And I listed across the bottom of this chart a number of those payloads that we intend to fly. In fact, number one, the Hydros, another water-based thruster, is currently on orbit. And matter of fact, we were just doing some commanding with that spacecraft just in the last few days, trying out this new Hydros water-based thruster that is built for us by a company called Tethers Unlimited. Unlike the water-based propulsion system on OCSD, which we just simply heated the water up, this one hydrolyzed the water. It just splits the water into its hydrogen and oxygen components, and then we burn that gas that comes from that hydrolyzation. There are some other experiments, and we will launch these every 6 months that are coming up that will go on board that Pathfinder technology demonstrator. Number 2 is called HyperExact. It's a new attitude determination and control system that is being built for us by Blue Canyon Technologies in Colorado. Of course, pointing is everything when it comes to science. And so the more accurately you're able to point spacecraft, the better science you can usually get with a spacecraft. And so that's the point of the number 2 item there, called HyperExact. Number 3, a high bandwidth laser communications. I mentioned OCSD was able to demonstrate 200 megabits per second. We're working on a new laser comm package that can go on these small spacecraft that can give us 200 gigabits per second. And we're working with Massachusetts Institute of Technology and Lincoln Labs on that one. And that's probably going to fly on one of these PTD buses next year. 4 is an O'Mara reflector wave for a communications radar. We're still in development of that one, but the one I'm interested in the most to fly is the one at the end that's called Lisa T. And John Carr is the principal investigator on that at Marshall Space Flight Center. And that is if you think about the art of origami, and this is a solar array material that has a bunch of S-band transceivers all over it, and you fold that all up into just this 1U size, and you can put it into 1U of that PTD bus that's on the left. And then when you get on orbit, you open a door and this thing pops out and it unfurls. And the most impressive thing about it is the power that it generates out of such a material that's you can fold into just 1U. You get almost up to 600 watts of power out of this. It's an impressive new technology that I'm looking forward to demonstrating. And then if it's successful, then we'll be able to hand it over to the NASA Science and Mission Directorate for incorporation into future missions. Now, I spent a bit of time talking about PTD on the left. Let's talk about CPOD on the right. We still intend to launch this one later this year. And what you see there are 2 spacecraft that are also 3U in size. And this is the first time we're going to demonstrate autonomous rendezvous and proximity operations and docking of 2 3U CubeSats. And the docking mechanisms, there's a mechanical fingers on each end of these 3U size spacecraft, but there's also an electromagnetic mechanism which we turn on as the spacecraft get close to one another. So we're using mechanical and electromagnetic docking mechanisms to bring these 2 spacecraft together autonomously in orbit. Now, here's just a quick review of some other upcoming CubeSat class technology demonstration missions. I'll start with the one on the right because that one's on orbit right now. And those are 3 1U size spacecraft. And the intent there is to do risk reduction for future swarm missions in which we think it's going to be necessary to demonstrate autonomous ranging and communication and network and ad hoc network communication set up among swarms. And so those spacecraft are in orbit now, and we're actually working with those at the present. Now, let me go back to the one on the left. because this one we intend to launch probably early next year, and it's called the Advanced Composites-Based Solar Cell System. This one is a 12U size spacecraft, and you fold all of the solar cell material into part of the 12U, and when it gets on orbit, these booms unfurl, and then that solar cell material unfurls as the booms are extending from the 12U size spacecraft. The material in this case is not the technology of the cell itself is not the technology we're working on. It's the boom material. It's a new composites-based boom that during its time on orbit should not warp nor twist as we've seen metal booms do before. And so this one is going to launch early next year, and in certain lighting conditions, because this thing is pretty good size, it's about 81 square meters, you may be able to see it with the naked eye from space, getting some glints of light coming off of it if the lighting conditions are appropriate. The second one that you see here is called Starlink, and this is a much more capable demonstration of a swarm mission. There will be 4 spacecraft that we launch at one time, and these will do autonomous formation flight among the swarm, which we think is going to be an enabling capability for swarm missions for the future, particularly if you want to do multi-point science data collection around a science object of interest. Now, the third one here, CLIC, CubeSat Laser Intersatellite Crosslink. I mentioned earlier with the optical communications and sensor demonstration, we did a demonstration of laser comm from spacecraft to ground. And this one we're going to do between spacecraft. And we're using commercial off-the-shelf parts. So we're not getting the high data rate we did with OCSD, but it's 20 megabits per second. It's pretty decent. But we just want to show that we can build 2 3U size spacecraft and put the optical components on board that are basically used commercial off-the-shelf components, and put together a pretty decent little demonstration of CubeSats doing optical communications between each other. Now, these are 2 show-classed demonstrations that are coming up. These are very important to us, and these are going to launch this year. Let me talk about the one on the right first. Capstone. Cislunar Autonomous Position Technology Operations and Navigation Experiment. Yes, that's a mouthful, NASA. We love our acronyms. But this spacecraft is very special because it's going to be launched on a Rocket Lab rocket called Electron, and we're going to launch this from New Zealand, and it's going into a very special orbit. And I mentioned that in the caption there at the bottom of the image, a near rectilinear halo orbit. That is the orbit that we intend to put the next space station in, called Gateway. No one's ever flown in that orbit before, and it's a very special orbit between the Earth and Moon. It has a libration point that allows it to oscillate back and forth between the Earth and the Moon, and also maintain constant communications between potential sustained presence sites around the lunar South Pole and the DSN, or the Deep Space Network, on Earth. This one is scheduled to launch in late September of this year. And once it gets injected into the near rectilinear halo orbit, we'll be conducting ranging experiments between a spacecraft that's orbiting the Moon today, called the Lunar Reconnaissance Orbiter, and ranging between the Deep Space Network on Earth. And that will let us do a characterization of that near rectilinear halo orbit to prove that the orbit is as stable as our mathematical models say it is before we put Gateway into that orbit. Now, the one on the left is a 6U class spacecraft, and it's going to be dropped off around the Moon when Artemis 1 launches later this year. It is one of 13 secondaries, or 13 small satellites, that are going to be taken for a ride on the Artemis rocket, also known as SLS. And a number of these are going to be dropped off either along the way or around the Moon, or dropped off in a Earth-trailing heliocentric orbit. But this one has a very special laser head on board as its payload. And we're going to make a number of orbits around the Moon with this 12U size, the 6U size spacecraft, and we're going to irradiate a number of the craters in the South Pole to determine the prevalence of water that's trapped in those darkened craters. And so we're looking forward to this mission being completed because we've proven already with a couple other missions that there is water on the surface of the moon. Now we want to understand the prevalence of it in these craters that are on particularly in the South Pole area. Now, before I switch gears on you, I just want to give you once again just an overview of what we're trying to do in our small spacecraft technology. We're trying to basically enable spacecraft to extend beyond low Earth orbit and be used in cislunar and planetary space, and enable some new mission architectures with the technology we're developing, either with small businesses, with industry, or with universities. We think we can use this to basically enable or augment existing assets in future missions with supporting small spacecraft for those missions that could be going out into planetary space, and basically get them into new destinations. We've only been into planetary space once before with the Marco spacecraft that, as I mentioned earlier in this presentation, escorted the InSight lander to Mars. So this is what we're trying to do with small spacecraft technology. But you can see from this chart, and you can see at the bottom right, this is our operating and future NASA Small Sat and CubeSat fleet. And this is color coded. You can actually download this from the NASA website on how we're embracing small spacecraft to help us do Earth science, heliophysics, planetary science, and astrophysics. And also we use the technology that's coming out of these different pipelines to enable those different missions. And I mentioned earlier that one thing I want to talk about in this presentation was Kepler, and is the introduction said that this was the one spacecraft that was specifically designed and tuned to detect exoplanets, planets beyond our solar system in the Milky Way galaxy that could be potentially habitable, like Earth. And we decommissioned the spacecraft in November of 2018 after a 9.5-year mission. And one of the things that I was looking forward to, and it took us 2 years after decommissioning because we had to analyze all the data. And I hope you're still there because my screen collapsed for a second. But
yes.
All right, one thing I was looking forward to, and it took us 2 years after the mission to be completed to go through all the data, and we released this paper, and I think it's one of the most important papers that came out of the Kepler mission. And it was released in just 3 months ago in December of 2020. And this is called the occurrence rate of rocky habitable zone planets around solar-like stars from Kepler data. One of the things, and of course there's a busy eye chart here, and I don't want to spend a lot of time on this, but the thing that you need to understand as the final results from the Kepler mission is this: go outside at night, get away from your city lights, and get away from all the light pollution. And if you're able to do that, look up in the sky, and this is what you can understand as a result of Kepler. Every star has at least one planet, and 1 out of every 2 sun-like stars has an Earth zone, habitable zone Earth-sized planet in it. That to me was astonishing. So if you think about that, that's 200 billion stars in the Milky Way galaxy, and there's a certain percentage of them that are sun-like stars. There's a huge number of Earth-sized habitable zone planets are out there. But of course, we don't have the technology today to get there. We don't have warp drive like Star Trek, if you're a Star Trek fan. But it also gives us an idea of the potential for life to exist throughout the galaxy. There's one thing I want to mention, that there's some very unusual discoveries that came out of Kepler. People used to think that planets could not form around binary star systems, and we proved that they do. But now we have evidence that they actually form around trinary star systems. And KOI5AB was one result that was announced not too long ago. And it shows that we have now, from the Kepler data, we discovered an exoplanet that is inside of a trinary star system. To me, that was impressive because it changes our interpretation of how nature makes planets or planetary systems. There's not a cookie cutter to this at all. And nature is going to make planets however nature wants to make them, and it has made a menagerie of planetary systems out there. And many of the discoveries that we found from Kepler were mind-boggling, particularly when you think about how many Earth-sized habitable zone planets are out there now. Now, I just want to switch gears on you quickly and just talk about a couple of things that you've been aware of recently. Of course, there's the recent landing of Perseverance into the Jezero crater, and this is a false color image of the Jezero crater. And you can see the ellipse there where Perseverance landed. And the key goal of this mission is to look for rocks that could preserve biosignatures. Biosignatures, of course, is a catch-all term for many different types of records. I'm reading this for you. Of ancient life, everything from isotopic hints of living chemistry to actual fossils. This Jezero crater, as you can look at this, there is evidence that there was at one time a water on the surface of Mars. And you can see that canyon to the left, in which there appeared to be a canyon in which water flowed into the crater. If you look to the right, the appearance of another canyon in which water seemed to flow out of it. And that ellipse there on the left is where Perseverance landed. You may have seen this image is just released within the last couple of days. We're going through, NASA's going through the initial checkout still of the rover. And I love this image because it's pretty high definition cameras that we have on board right now. And of course, we're taking pictures all around the rover to make sure everything is fine. And we're moving the instrument arms around to make sure it's okay. But the thing that a lot of people are looking forward to, even though it's not meant to conduct science, is still a technology demonstration, is the flight for the first time of an aircraft through the Martian atmosphere. That little helicopter is slung underneath the rover, and the arm is going to pull the helicopter out, and we're going to put it onto the surface of Mars, and the rover is going to back away to a certain distance. And this thing is solar powered, and so it's going to charge up, and then we're going to fly this helicopter around in the Martian atmosphere. It won't be the last time we do this, but this is a technology demonstration. It'll be the first time that we have done it to show that we can fly an aircraft through the atmosphere of another planet. Later this decade, in the year 2027, we have another larger helicopter that is going to be sent to Titan, that the largest moon in the solar system, and we're going to fly a quadcopter through the atmosphere of Titan, which is going to be, I think, quite impressive. But you got to start somewhere. And of course, this is where we're starting with Ingenuity. That's the name of the little helicopter that's going to be flying through the Martian atmosphere in a not too distant future. Of course, these little two bios you see here being loaded under Perseverance, those are the science instruments that are going to be used to capture samples from the bottom of the crater, and those are going to be cached at some place on Mars. And then later on, we're going to send a mission later this decade to retrieve those cached samples and bring those back to Earth. You probably saw some news recently about the OSIRISRex and its collection of the sample from the asteroid Bennu. And this is the actual image of that collection. The spacecraft is now departing and is on the way back to Earth, and it's almost a 2.5-year cruise back. And then we're going to capture the reentry vehicle that's coming back from the spacecraft, and then examine the surface material that this spacecraft collected from Bennu. Later this year, of course, I mentioned this rocket earlier in the presentation, Artemis, the SLS, is going to leave Earth for the first time. I think the potential launch date is November, and it's going to carry Orion out beyond the moon, and Orion is going to come back. That's our next spaceship. And the other thing I want to make sure that you're also aware of, and this doesn't get a lot of press, is this mission called DART. And this launches late this year too, and it's going to Didymos. DART stands for Demonstration of an Asteroid Redirect Test. And we're going for this little binary asteroid system called Didymos, and we're going to impact the smaller object you see there on the right. And we're going to see if we can change the trajectory of that little moonlet that's in part of this Didymos binary asteroid system. And you can see another object there on the lower right-hand corner. There's a little CubeSat that's going with the mission. This one is built with the Italian Space Agency to observe the impact of the spacecraft onto that moonlet. And we'll be observing this with that little spacecraft and also with telescopes from Earth, because we want to prove that you can do a direct asteroid redirect by impacting it and then measuring the change in the orbit of the object in case we need something like this in the future to deflect an asteroid that may be on a collision course with Earth. Of course, I love this image. This is courtesy of Jim Vaughn, who is a techno artist. And this is an image of the James Webb Space Telescope. This is the follow-on to Hubble. This thing is huge. And it's the collection mirror is about 6 times the size that of Hubble. And this is going out to Lagrange point L2, about 1 million miles on the other side of the moon. And this is the scheduled launch of this is also late this year. So we have a number of missions that are coming up late this year that I think you might find interesting. And I just want to leave you with this this image of India from at night. And I think we have time now to take a few questions. And thank you for your time and your indulgence for letting me speak to you tonight about small spacecraft, a little bit on the aftermath of the Hubble mission, and a little bit on some missions that are coming up that I think you might find of interest. So thank you very much.
Thank you, sir. Thank you, sir, for sharing this wonderful information with us. Now, with your permission, we would like to move to question and answer sessions. Okay. So the first question is, as we know that stranglets are the most dangerous particles come out in the cosmos by collision of 2 neutron stars. Is there any technology on NASA working to detect stranglets by telescope or other technologies?
I'm not aware of any. There may be. It's NASA has a lot of technology development going on across the agency. And as a matter of fact, my little program, Small Spacecraft Technology program, is in the Science and Space Technology Mission Directorate. And that directorate has about a $1.6 billion a year budget for investing in interesting technologies. And it's interesting to me just to sit in on their monthly meetings. And I'm there just to brief the status on what we're doing in small spacecraft. But I get an exposure to a number of other things that NASA is working on. But the particular area you're mentioning, I'm not aware of any at this moment. There may be. I probably have to go do some more homework just to see, because sometimes it's mind-boggling to me how many things that NASA is investing in, either by itself or in partnership with the European Space Agency.
Okay. The next question is, theoretically, we have ensured the presence of Planet 9. By what is plan of NASA to find it and to capture image of Planet 9?
Oh, that's a really good question, because a number of the scientists I work with on Kepler are kind of interested in that planet. There's evidence of something out there. As a matter of fact, Dr. Natalie Battaglia, who is one of the mission scientists on Kepler, was quite intrigued by this. There, you could see, from what I understand, and I'm not an astrophysicist. I'm more of a I'm a mathematician and physicist, not an astrophysicist. So there's evidence within the Oort cloud and the Kuiper belt of something that has a gravitational effect on them. And so I know that Dr. Natalie Battaglia has encouraged some of the other astronomers out there to see if they can point to a particular slice in the sky where they think this object is, and see if they can get an image of it. You think about, for example, Pluto, and is considered now a dwarf planet. I guess that's a new characterization for it. Yeah, I guess it was named a dwarf planet in 2006, and that made a lot of people angry because they like having a 9-planet solar system. And Pluto was detected because another astronomer was seeing movements within the Kuiper belt as well. And he said, there's something out there. And he encouraged a couple of astronomers to look in a particular direction. And Percival Lowell was one of those. And that's how they found Pluto. but it took a long time before we got decent images of Pluto. And I don't know when we're going to see any evidence other than the gravitational impacts of Planet Nine, but I'd be interested if somebody's able to find it. I'm sure it'd be intriguing and be quite a discovery. Are you still there?
Am I audible, sir?
Yes, I can hear you.
Hello.
Yes.
Question is, what are the dimensions of the small spacecrafts and how are they retaining their positions in the atmosphere?
The dimensions of a small spacecraft are anywhere from the 1U size that I was mentioning earlier for OCSD. None of these are meant for atmospheric. They're all meant for orbital trajectories. But there's a definition for what is a small spacecraft. And NASA considers anything 180 kilograms or less as a small spacecraft. And I think where they got that from was, how much mass can you hang off the side of a port on an Esper ring? And right now, I think on an Esper ring, that's probably about as big a spacecraft as you can hang off the port of one of those objects that you put inside a rocket that allows you to carry secondary payloads into orbit. But small spacecraft are 180 kilograms or less, according to the official NASA definition.
Okay, so they are really very miniature. It's only 180 grams. Yeah.
Yes.
So the next question is, the participants want to know about the water propulsion system used by NASA in some of the spacecrafts.
Well, so far, it's the one we use on OCSD was it wasn't very powerful, and we didn't need it to be powerful, and it was just meant for a technology demonstration. And of course, when you look at those OCSD spacecraft, they were 10 by 10 by 15 centimeters, and they only weighed about 2.5, 3 kilograms. They're very small, but this thing was packed with electronics, probably the most densely packed spacecraft we ever built. And we couldn't put a lot of water in it. We didn't need a lot because we just needed enough that we could heat up and let those little spacecraft put around each other. When you're out there in space, it doesn't take a lot of propulsion to move something, particularly when you're moving it in just relation to another object that isn't that far away. The hydro thruster I mentioned, it hydrolyzes the water. It breaks the water molecule into hydrogen and oxygen, and then we burn that gas.
Okay, so the next question is a bit a political one. Why doesn't space agencies work in coordination all together, like NASA, ISRO, European space agencies, for better research and breakthrough innovations at a quicker rate?
Well, they should. I mean, you go look at the International Space Station today, and there are 10 partnering countries on the International Space Station. I look forward to an arrangement between NASA and the Indian Space Agency. Why don't we have one? We should. And I would think that we should have, for the next, if we're going to have another International Space Station, I would like to see more space agencies participating in it. The International Space Station today has been very successful because there have been a number of countries participating in it. But you probably saw there was a meeting recently between India, the United States, Japan, and Australia. Those are 4 democracies. And of course, the meeting was more politically oriented. It was mainly meant as a discussion so that there can be a counterweight to China. But why can't more countries be collaborating with each other in space? Because one, I think you can get more bang for your buck. And also you can bring some of your best scientists together from all the countries. And so you can solve a lot more problems together like that. 2 heads, 3 heads, 4 heads is better than 1 head trying to solve a problem.
So the world is moving towards globalization, we can say.
Yes, absolutely.
Yeah, sir. The next question is, possibly how much time will it take mankind to find new habitable home, according to you?
Well, that's a good question. That's one of the things that we want to find life elsewhere off of the surface of this planet, mainly because it's one of the scientific objectives of one of our roadmaps. Matter of fact, if you look at the NASA astrophysics roadmap, it's guided by 3 questions. One is, are we alone? The second one is, how did we get here? And the third question that's in that roadmap is this, how does the universe work? Now, Ellen Stofan, who is a former NASA chief scientist, she predicts that we're going to find definitive evidence of life beyond the surface of this planet within the next 2 to 3 decades. But the question then becomes, where is the human race going? Of course, there's talk of having sustained presence on the moon, and then Elon Musk and guys like that want to go to Mars. Matter of fact, Elon is famous for saying he wants to die on Mars, but not on impact. But when it comes to interstellar travel, that's that's a science fiction right now, and everybody's probably seen the movie The Martian. Trying to live on Mars is not easy. It isn't. I mean, 1, you can't breathe the atmosphere, and 2, it's very cold, and 3, I don't care how much poop Mark Watney used, it's hard to grow stuff into soil on Mars because there's perchlorates in that soil. And so, but where there's always a will, there's a way, and it depends upon subsequent generations building upon the discoveries that we're making today, and what will they do with those discoveries. I foresee that you're going to have, right now we already have a sustained presence in space with the International Space Station. There's been a sustained human presence in space now for 20 years. Your generation basically is a new aspect of evolution of humankind, because now we're living off the surface of the planet in a permanent way, even though you have to resupply that space station on a regular basis. But who would have thought back in the times of Columbus and the early sailors that no one ever thought we'd be living in space 300 or 400 years ago? Where we're going to end up in 300 or 400 years from now if we don't kill ourselves on the surface of this planet, and we don't ruin the planet with what we're doing to it today. But we're counting on generations like you and the ones that come behind you to help us solve some of those challenges today, so that we can extend the evolution of the human race.
The next question is, just a moment. What are your views on the Starlink mission directed by SpaceX, and how will it modify the current communication and internet technology?
Oh, it's of course, Elon is quite a visionary.
Yeah, that's right.
We work with Elon quite a bit. As a matter of fact, we buy a lot of his rockets. And matter of fact, we just awarded him a contract to launch the first 2 elements of the new Gateway space station. And Elon has a vision for a number of things. Not only is electrification of transportation and providing clean and efficient power on the surface of the planet, but he's putting Starlink spacecraft up there as providing space-based internet, because he wants to provide information to the surface of the entire planet and make it more accessible to everybody. It's interesting you bring the question up, because just this weekend there was a conversation in which I have a new technology demonstration that's going up not too distant future, and we're injecting it into the same orbit that Starlink goes into, and people were worried about that. Says, wait a minute, that's where Starlink goes. And said, well, I mean, he doesn't have a monopoly on that orbit. I mean, other people can go in that orbit too. But the thing that it brings up, Starlink is emblematic of the democratization of space. When you think about it, there's only 2 countries that used to be able to launch things into space, and that was the former Soviet Union and the United States. They were the 2 premier superpowers on the surface of this planet. Now, look what's happened. There's over 80 nations have satellites in space, and there's a number of nations that have the capability to launch into space. And of course, you have now a number of countries that have space agencies, and now you have commercial companies that are launching into space. This is where we're headed. Starlink is just emblematic of that. The question is going to become in the future is how do we all share the common ground? That's going to be the thing that we're going to have to face, particularly as more and more of us are going to be orbiting spacecraft, and we all want to be able to transmit on certain frequencies. So there's going to be there's going to have to be some more discussions, international discussions, to address those coming issues.
As you mentioned that other peoples are also putting or locating their satellites in the same orbit as Starlink satellite. So how are they managing the space traffic, sir? With the help of GPS or any other techniques?
Well, they're using GPS. A lot of these spacecraft are going up now. They have GPS receivers on board so that we can get a good fix on where they are. But it's going to become more problematic because just as we have on the surface of the planet, we have, for example, in the United States, we have the Federal Aviation Administration working with counterparts in Europe for managing air traffic across, the land masses here in the air environment. You're going to need the same thing in space. And the Department of Commerce in the United States has been assigned that duty as, I guess, to call it the space traffic cop. But it's going to take more than one agency is going to have to work on the rules of the road that's going to allow us to all operate safely in not just low Earth orbit, but these other orbits that are above that. Because as these people, as the low Earth orbit becomes even more densely populated, you're going to see these move out into deeper orbits. Middle Earth orbit, where GPS operates today, and also into the geosynchronous orbit, where many countries are operating today, just to provide space-based communications from that position. You're going to have an international group that's going to be working this issue on a regular basis.
I also think the same, that a UN-like body should be formed which will manage the air traffic so that all the countries can come together and manage them, because there are no specific borders in this space.
That's right. And matter of fact, when you look at the laws in space, they're different than the ones, for example, on the high seas.
Yeah.
You can't go up and grab a rocket body and just pull it back and get it out of orbit, because that rocket, once it's launched, is owned in perpetuity by the country that launched it. And it's not the same as on the high seas. For example, on the high seas, you find something's been abandoned, you can salvage that. Not so with space. So there's going to be some changes also from a legal aspect.
So the next question is, there have been rumored clips of possible UFOs having no propulsion technology visible and still flying around the sky at speeds not humanly possible. In how many years, according to you, will humanity be able to develop such technology?
Well, I'll just tell you a story. Back in the 1980s, of course, here in the United States, the Area 51 place is legend for, the secret spy planes and things they develop and fly over there. And of course, you can't get there now because it's prohibited area. But at one time, people used to be able to get kind of close to it, and they would take pictures and they would talk about, these bat wing planes that are flying out of Nellis Air Force Base or Area 51. And then one day, one crashed. And then, the secret's out of the barn because everybody went to the crash site and everybody had pictures of it. And no one ever seen a plane like this before. And that was where the F-117, that's when the F-117 came out of the closet. So you think that's the last thing that's worked on in these places? No, there's, I'm sure that, there's laboratories that are working on, the next generation, super duper planes, whatever. Of course, UFOs are UFOs, it's unidentified flying object. You can go out in the sky and look at something right now, and you don't recognize it. You could call it a UFO. Have I ever seen one? No. I would love to see one. As a matter of fact, people always say NASA is keeping us a secret. If NASA came out and said, we have definitive evidence of UFOs, our budget would go up dramatically. So we probably could use, I'm joking with you right now, but it's, you get to the point where there's the laws of physics on what you can and cannot do. And you have to obey the laws of physics. And people, you see, I love these science fiction movies in which time travel and faster than light speed are exhibited like they're like second nature in these movies. But a lot of those things violate the laws of physics. Maybe, however, there's one student on here today in this lecture who's going to come up with prove that one of the laws of physics is actually not as concrete as we may think it is. So your generation is going to help us extend that. And there's one thing I wanted to do tonight before, I know we got, I don't know how much more time we got, but I always give, recommendations to students for books to read that are going to open your minds. And this one I read is J. Craig Venter, and I'm not advertising this, but it's called Life at the Speed of Light, From the Double Helix to the Dawn of the Digital Life. And this guy is a genius. And he has an organization down in San Diego right now, and he's cataloging the genome of every living thing on this planet. And he was one of the Nobel Prize winners back in the 90s when they first sequenced the human genome. And you should read books like this because it's going to change the way that you view the world and also view the way that science and technology is developing. There's other things that you probably should become more versed in, and that is artificial intelligence and machine learning. And if you know of Max Tegmark, there's one book I would recommend you read. It's this one, Life 3.0. Being Human in the Age of Artificial Intelligence is the name of that book, because there's a lot of things that we're going to have to think about as artificial intelligence becomes part of our lives in the decades to come. Particularly, we have to start thinking about how artificial intelligence is going to be ingrained in the way we fight wars, or the ways that we develop our economies, or in the ways that we manage our transportations, or how they impact the way that we administer medicine in the future. There's going to be, what will the changes be to our laws as a result of artificial intelligence? There's I'm sort of getting long-winded and going on different tangents here, but there is, we're relying on your generation to help us solve so many issues. Climate change is real, and it is a significant challenge that we're going to have to face. And concomitant with that is biosphere collapse. And those are serious issues. And the developments that we're making today in science and technology are some of the things that are going to help us or give us the tools that we can address those challenges for the future. And this is another reason why I think we need to have a lot more international collaboration, because these issues that we face, from climate change to biosphere collapse, these are international, these are global issues, and we're all going to have to solve them together.
We should act as the citizens of the world. That will help us.
Yes, exactly.
Yeah. So the next question is, as the project manager for NASA's first mission for finding potentially habitable planets, which would you say looks more promising for human habitation, the moon or the Mars?
Oh, well, the moon's easier to get to, but there's no atmosphere there, but there's evidence of water. We have evidence of water on Mars. Eventually, because the more, I guess you would have to say, because of the ability to do more terraforming with Mars than the moon would probably in decades to come would be more enticing. But to learn how to live there, you want to be able to learn how to sustain yourself in an area that you can get to easily back and forth, because it's only like 2.5 to 3 days to get to the moon. It takes us over 7 months now to get to Mars. And there's certain times of the year where Mars is out of the question because of just the orbits of the planets. The moon is, of course, always going around the Earth, but Earth and Mars are going around the sun on separate orbits. So I'd want to learn how to live on the moon first before I went to Mars. And that's what the intent's going to be. That's where we're headed, apparently.
So the next question is, how has the technological advancement in computers helped in the space exploration and the astronomy?
Oh, without question, it's been dramatic. NASA created the information age. mean, all the students on this lecture today have smartphones, I guarantee you. I bet you every one of you has a smartphone. You have more processing capability in that smartphone, far more processing capability than we have with the computers that we put on Apollo. Because you go look at Apollo, the computers we had on there were capable of about 85,000 instructions per second. That's a joke compared to today. I mean, you go look at your smartphones today, and those things are capable of trillions of instructions per second. I mean, your generation, you're spoiled compared to what we had with Apollo. But people ask me, what is the most important thing that came out? Is the information. A short amount of time to get to the moon. And but the most important things, of course, were those computers, and those were hand built. They were hand wired, and we employed people with very small hands to actually do the hand wiring for those computers. And so there's no doubt that the computer age was born out of Apollo, and the information age came with it, because people like to talk about the images from Apollo of Neil Armstrong putting his feet on the surface of the moon, and those iconic images of those guys walking around that surface. But when you look at Houston, you look at all those computers that were used to help manage that mission, I said, that's probably more emblematic of the impact of Apollo on society than anything else. It was basically the information age was born out of that.
So the next question is, have you find any habitable orbits or habitable planets in the solar system?
We're standing on it.
Other than Earth?
No, it's, if you ask Frank Drake, the guy who basically came up with the Drake equation, if you know who he is, he's in his 80s now. And he's the guy who basically posited the Drake equation back in the early 60s. And he was trying to estimate advanced cells that could be scattered across the galaxy. And we were having this discussion one time about the habitable zone. And he said, our definition of the habitable zone was too simplistic. He said, go think about this. He said, if there could be life forms living in the clouds of Jupiter that we have no idea what they are like, because they're not Earth-like. And he said that we need to change our thinking about habitable zone to a different perspective. And because he said, you look at Earth itself and the extremophiles that we have on the surface of this planet, and things that live in the acid pools of Yellowstone National Park, to the worms that live deep in the ice of the Arctic. He said that, habitable zone could be in areas that we wouldn't expect. And I said, yeah, but I said, from the Kepler perspective, we want to determine, are there other potential worlds like Earth that are out there? And I said, that would give us an idea of the persistence of life in the galaxy. And he said, yeah, you got a point. But he said, sometimes, you got to have those kind of simplistic ideas before you can you go to more complex ones. He says, all I'm trying to do is ask you to think that there could be other areas within our own solar system that are habitable, but not necessarily by humans, but by life forms that we have no appreciation for.
So the last question, but many of the students have repeatedly asked this question, that how can one join NASA as an astronaut or as a scientist? This is one of the most common question I'm getting today.
Well, let me put it this way. To work for NASA, we advertise all of our jobs at usajobs.gov. But unfortunately, in this case right now, there isn't an official agreement that exists between India and the United States. And this is what I would recommend, that your prime minister work with our president and see if there can be some agreements that could be fashioned that would allow astronauts from or engineers from India to come work at NASA. Right now, I cannot take international interns from India, even though I'd love to take some international interns from India. I've had some from other countries, and they're basically ones that are part of the European Space Agency, and there are nations that support the European Space Agency. But I'd like to see that it extend to India. You're the largest democracy. I mean, look, you got 1.3 billion people there, and you're the largest democracy. Yeah, and you have a lot of good engineers and scientists. You have the ISRO. Why can't we have some bilateral agreements between the United States and India so that we can take some of your brightest engineers and bring them over here and work with NASA, and also have an exchange program in which some of our engineers also go work with ISRO?
I hope that Prime Minister of India and President both of America both would make some treaty, so you could get some Indian interns. Okay.
Yes, and I hope you guys invite me back, because I want to come and visit India again. I've only been there once.
Sure, sir. Yeah, so now I would like to thank you, sir, for being so patient to answer all of our questions and sharing this valuable information with us. I'd also like to thank Chetan Limbasya, sir, for being here, and to all the participants to being patient and asking questions. Okay, thank you, everyone. Thank you, sir.
My pleasure. Thank you. Are we done? Okay. Good night.
Good night, sir.
Good night.
That's